Good afternoon. Today we are going to start the sections on recursion. And so before we do that, let's just recall the organizational structure that we went over on Friday, which is not in the book, but which is representative of the new style that is part of any good C++ library. Okay, so again, this style is not in your book, very much like the operator plus equals and the operator plus. That style was also not in your book, but in lecture, that is the style that I am demanding from you, and in particular on the exams, that is absolutely a type of problem on an exam. I could demand you write a solution which uses the style from the course. Okay, so let's just very quickly recall what that was. And that was to take pretty much the code verbatim from your book, which was written in a very procedural style of open a file, test to see if it was found, grab the data from the file, call a close on the file to release the resource. And what we've done is we've sort of C++ified it. Okay, we've object-oriented it. We've locked everything up inside of objects. We've worked with constructors and destructors in a way that hides all of those implementation details, so we don't have to rewrite them each time. Okay, so let's recall the read from file. So the read from file says give us a file with data that we're going to read from, and we're going to construct that object using here it is, using this constructor right here. So we're going to give it a string with a file name. And then this constructor is going to initialize the ifstream object fin, we've called it fin, using the file name. And it's going to check in the constructor to see if the file was opened or not. Okay? This way, all we have to do is give it the name of the file, and automatically, based on the way we've constructed the object, each time it will then check to see if the resource was available. Similarly, in the destructor, it calls fin.close for us, so that all we have to do is create the object, the file object, work with it however we want, and then just like when we create ints and doubles on the stack in main, we don't have to do anything extra. The operating system automatically cleans up for us. Okay? Then what we've done is we've overloaded the operators so that when we read from a file, it treats this file object just like a cin, except instead of getting input from the console, we get it from a file. Okay? So everything from last Friday was about attempting to mimic console input, console output for files. And not just for files, but with the idea in mind of, okay, well, this really should apply to any type of stream object. Okay? The underlying fundamental, the base class of all of these is an OStream and an iStream class, which underlies this idea of grabbing, putting characters into a string of characters, and then taking that set of characters and taking them out and interpreting them in a certain way. So instead of working with the console like we've been doing, now we're going to transition more towards files, which is a little bit more realistic. This is more of what I do. If I want to run a simulation, usually I have some input data, for example, a set of XYZ coordinates of a lens. I'm going to do something with that data, and at the end of the day, at the end, I'm going to have this collection of numbers. I want to output that to a file as well. Okay? So here we have the infrastructure to make that just as easy as if we're working with cin and cout. Okay? Then we overloaded certain functions. So we overloaded the operator, for example, to grab the digits one at a time. But if it was a set of tabular data, a data with one row at a time, we overloaded the functions called getRow. I think there was another one as well. Let's see. GetRow and getLine. And the idea behind getRow and getLine was to take these ideas, this idea, for example, of grab the entire first line of data, which is formatted to be numerical number space, numerical space, numerical space. And rather than think about extracting that line as a string, which was the first one, we really want to just go directly to take that first line and store it as the elements in a vector, each individually converted to a numerical value. Okay? And that allows us to more elegantly work with this class, which reads from a file and can allow us to very quickly and easily extract numerical data, even though it's really just storing a collection of characters in an ASCII format. Okay? So that was the idea. This is a very profound idea. It's a very fundamental idea, which I am going to be imposing for the rest of the quarter, this idea with files, input, output. You're going to need this for your next homework that's due on Friday, and you're going to need it for the following homework. Trust me, the next homework will be a lot easier to implement and work with if you follow this paradigm. Okay? So you have well, I'll be posting the code soon. I haven't posted it yet, but I'll be posting the code from Friday, and that way you can use that as a reference for when you write your own code. So like I said, today we are going to begin the chapter, I think it's chapter 9, on recursion. So we kind of did a little detour. We went to chapter 14, and then, or is this chapter 10? Does anyone know? Well, anyway, we did operator overloading first, and part of the reason for that is to get much more familiar with working with classes again and objects and object-oriented design. We've gone now to class inheritance, and then resource management, virtual destructors, making sure there are no memory leaks. And now we're going to push to a greater depth in programming, which is, all right, you have a task you need to solve, a task to complete, a problem to solve. You're going to have many different ways of thinking about it. Recursion is a very powerful technique that if you understand correctly, it can unlock very fast and efficient algorithms. Okay? The emphasis in this class is not about how cleverly you solve the algorithms, but it's about understanding them and then knowing how to unlock them in C++. Okay? So with that in mind, let's do a really fun example and a very fundamental example. It's called Towers of Hanoi. So this is in your book, and you've probably heard of this if you, maybe even in elementary school you heard of this problem. You start with 3 rods and a stack of disks of decreasing size placed one on top of the other. You move one of the topmost disks to another rod, but it can only be placed on a new rod if it is less than the smallest disk on that rod. In other words, you can't place a larger disk on top of a smaller disk. Okay? And you can only move a disk if it's on top here, just like a physical object. And you can only move one at a time. And the goal is to get all the disks here into, say, that column over there. So if you have one disk, let's do it again. Done. Okay? So you just take it, you move it. There's no other disks of smaller size. You just move it. 2 disks. This is going to be a fun set of slides for the first part. Okay. Now, how do you do this? You take the topmost one, you put it there, you move the other one, you move the other one in place there. Okay? How about 3? Okay? So let's actually do this again. Well, let's do it again. It's fun. Okay. So the idea here is I need to move the top one somewhere. I need to move the next one somewhere. I can't put it on top of, there's only one place this thing can go, and that's right here. It can't be moved there, and it has to be moved, so it definitely has to go there. Now the larger disk, you could move the red one back on top of the black one, but that's just undoing the move you just did. The only real move you can do is to move that one on top of the green on top of the red, and then the only place to move the black is there. And then you're almost done at this point because you say, aha, well, all I need to do is get the green out of the way, put the red on top, and then green on top, and I'm done. Okay? Now, let's do this again, and in particular in the 3 disk case. But let's pay very close attention to the, I don't know if that's a word. Is that a word, repetitiousness? Probably it's not a word. Okay. But you get the idea, right? Think about what we're doing in terms of how the smaller set of steps mimics the larger global goal. Okay, so when I moved the green over there, that was actually a solution to the disk with the problem with one disk. Okay? Now when I move the red and the green in place like that, that's actually the solution to the problem with two disks, just with a different column. Okay? Then when I move the black one over, now we stop and think. Okay, slide. All right, let's see. The largest disk is in its right place, and now all we have to do is move this set of two disks into a third column, which is exactly the same problem that we looked at with exactly two disks. Okay? This black disk, now that it's in place, is irrelevant. It doesn't matter when trying to figure out how these other disks should be placed on top. So the idea is if you can solve the problem using a smaller number of disks, then don't think in terms of each individual move. Think collectively in terms of that smaller solution. That's essentially what recursion is. Okay? So let's think about 4 disks. Okay? Now, I'm not going to animate the entire process. I could, right? I actually considered animating the entire process just to work it out and show you how annoying it is. But I'm going to challenge you all to really internalize the fact that I don't have to. Okay? I've shown you how to move 3 disks around, right? So let me assume that you know how to move 3 disks into a new column. Okay? So ignore this larger disk, and let's move these 3 into that column there. Okay? Whether I move them to this column or that column, it doesn't matter. Okay? But let's just take the top 3, which we saw exactly how to do before, and we're going to assume that we can move those 3 into that new column. Now, what do we do with the black disk? Plop it over. And now to finish up the problem, what do I need to do? Exactly. Take these 3 disks and then move them to a new column, but I already knew how to do that. Okay? That's the essential idea behind recursion. Okay? So this is probably one of the most fundamental... we'll wait on the joke. This is a very fundamental idea, which is, and this is the hardest thing to kind of get through your head when you're starting to code up in recursion and when you're doing these problems. Don't think about the tiny little steps. Do not think about the tiny little steps. Just think in terms of the big picture of, if I can move 3, then I can move 4. How do I move 4? I do a moving of 3, I move a 1, and I move a 3. So I can do 4. How do I do 5? The same thing. I move the 4, which I just showed I could do. I move the 1 in place, and then I move the 4 similarly as before. Okay? But you don't want to, as soon as you get the pattern and you get this kind of chain reaction, you want to forget about all of those smaller steps and embrace the idea of assuming I can solve the strictly smaller problem. Okay. That being said, let me tell you a joke. A physicist and a mathematician are in a kitchen when a fire breaks out. The physicist grabs an empty pail, fills it with water, and dumps it on the fire to extinguish it. Fair enough? Okay. The next day, the physicist leaves a bucket full of water on the table. Seems like a reasonable thing to do. Okay. Again, a fire breaks out. The mathematician jumps up, grabs the pail full of water, dumps it down the sink, hands the empty pail to the physicist, and proclaims, "This is a previously solved problem." Okay? So there's humor in this story, but there's actually there's actually a profound idea here, which is sometimes if you don't want to think very critically about what's going on, and you can already have an out-of-the-box solution for a problem, you can sometimes just unravel some of the structure and run it through an already solved problem. Okay? That's what's being done here. We already know some previous structure about it, but we're going to pretty much dismantle that structure because we already have a path which we know will get us to the answer. Okay? So that's the idea here. It's the same idea, which is you have this structure and you have a previously solved version of the problem, and you need to figure out a formulation that gets you into that previously solved version of it. Okay? I tried to coin a term here, a nerdy term called a selfie. I don't think it's going to stick, but I can dream. All right, so a self-similar function. Or in other words, some functions or routines are self-similar in the sense that in order to solve them, we need to solve an equivalent problem of smaller size. Okay? So to solve them, you need to solve the exact same problem with a smaller input value. I wrote a thesis using that principle. Okay? So it's a very powerful principle. For the towers of Hanoi, once we know how to move one disk into place, we can move two. Once we know how to move two disks into place, we can move three. For 3 disks, it is easy to move 4. Once we can move 4, it's easy to move 5, etc., etc. Okay? So the algorithm is the following. If you want to move n disks, where n is any number you fix in advance, just pick whatever number you want, like 20, well, integer, positive integer, like 20, 100, okay? You move 99 smaller disks, then you move the largest disk into place, and then you move the 99 smaller disks on top of the largest disk. And because you know how to, well, did I show you how to move 99 disks? No, but the assumption is that if you can move 4 disks, you can move 5. And if you can move 5, you can move 6, and you can move, okay? So the idea is to solve this larger problem, I break it down into a smaller version of the problem, and I just assume I can solve those smaller versions of the problem. Okay? You also might have heard of this idea, it's called induction, where you say, oh, okay, if I can solve this problem on a smaller input, I can inductively solve larger problems. You can prove theorems using this technique, and you can also write algorithms with the same idea. It's kind of going in the other direction, in a sense. Okay. Here's an example. So how would you reverse the letters in the word recursion? Let's say you have a string variable, and it has the characters recursion. How would you write code in C++ to just reverse, in place, reverse all the letters? Someone just give me an example of what you would do. Yeah, in the back. Okay, so the suggestion is to move the last to the forward and push the other ones over. Okay, well, I mean, that's a thought, but what's that going to do? Eventually, it's going to cycle around, and it's going to be the same word. Yeah. There you go. Exactly. So what do? You take the first and the last, either using pointers or just accessing the indices directly, because you can just assume it's an std string, the usual string class. Okay. You swap the first and the last, and then you increment in by 1 and in by 1 on both sides. You swap those two. You increment in. You swap, and you keep doing this until they either meet or they crisscross. Okay. Now, don't keep going all the way, and you'll reverse it. Okay, but just keep going until they either meet or they're crisscrossing. That's one way to do it. How would you do it recursively? Think about it for another moment longer. there's your solution for the non-recursive reversing the letters. Okay? So we have a string word. We have a car temp. In order to do the swap, we're going to store a temporary value. Wait, do I have on the next? What's on the next slide? Yeah, that's really what you should be using. Okay, never mind. We'll get to that in a second. Okay, so you have a temporary value. Then you start at the first letter, and you look at the last letter. You do the swap. These 3 lines are synonymous with swap. Okay, so you're basically just rearranging. Okay, and then you do this for I equals 0 up until n over 2. Okay, and here's where you want the integer arithmetic slicing off the fractional part. Okay, so you just do this until n over 2 rounded down. So if n is odd, n is even, doesn't matter. This is going to work. Okay. Now, is size t necessary here? Is size t appropriate here? Yeah, and this is what I'm trying to really emphasize a lot is, yeah, size t is solely being used as a index for a string variable. Now, you could use int for a word of size 9, for example. That will work. Nothing horrible is going to happen. But at some point, right, you might try and call this routine on a very large string. And if you don't use size t, you might end up with a runtime error that is mystical because the code works just fine. The code looks fine. The only thing that's not fine is your understanding of the data types internally. Okay? So that's why size t is very, very nice. I can make this even more. This is really what you should be doing. You should be calling routines like std swap or just swap, okay, if you're using namespace std. The reason is because they sometimes take advantage of optimizations in there. They don't just have those 3 lines of code. They actually know they're actually very efficient ways of swapping 2 data types. So if you can, this is kind of the slick way to do it. I would prefer you to explore built-in functions like swap. I think you have to number include algorithm to unlock this. But this is better than writing out those 3 lines of code individually because A, you might mess it up, and B, this is a little bit easier to read. What are you doing? You're swapping the ith letter with the n minus I minus first letter. Okay? So this is not using recursion at all, right? There's no recursion here. Now, what is this? So what do those 2 columns mean to you? How would you interpret those? Look at the second line. We have recursion on one side and r on the other side. So what did I do to get the r on the other side? I took away the first letter, and I'm left with recursion. Now go to the second line. What did I do? I took the first letter of the remaining word, and I left appended it to the r. Okay? What about the next line? I took the current first letter, C, and I left appended it to the ER. And then I kept going. Each time, I took the current first letter, and I left append it to the letters on the other side. Okay? Or in other words, in order to call reverse on the word recursion, I took out the first letter R, and I did reverse on recursion, left appended to the letter R. Okay? That's the idea. Just look at that second line. Reverse of recursion plus R. Now, if you want to go through the entire process of how, kind of in your mind, how this would work, you can follow the chain down here. Because what it does is it will take the E out, and it will left append it to the R, and then essentially call reverse on the smaller word. But really, you just want to stop after that second line, which is in order to reverse the letters in the word recursion, you pull out the first letter R and you append it to the same function called on a smaller set of characters. And then you stop thinking. And the reason you stop thinking is because you say to yourself, well, wait a minute. If I have a word of length 1 character, how do I reverse that? It's already reversed. How about 2 characters? It's 2 characters. I take out the first one, and I just append it to the reverse of the word with 1 character, which is itself, and so we have the chain reaction now going up. Okay? So the recursive thinking is, how do I basically take something big like the word recursion, and how do I take out a small piece of it, call the same function on a smaller object, and then recombine what I took out with what I assume to be the complete solution to the original to the smaller problem. Okay? That's the idea. Here is some code. Let's do this together. Okay, so let's just recall that. Remember the substr member function of a string. The substr takes 2 parameters. It gives you the first parameter is the index of the character you want to start your substring with, and then the second parameter is not the ending index. It is not the ending index. It is the number of characters starting with that index you want to include in your substring. Okay? So this is very important because this is a common misconception on exams that usually gets points taken away. Okay? So again, starting index and the number of characters in total, including that starting index you want to include in your substring. So for example, if recursion is the word, then word.substr of 2, 3 is cur, because the index 2 is R has index 0, E has index 1, C has index 2, and we're going to take exactly 3 characters, C, the U, then the R. So word.substr would return a new string with the characters C, U, R. Okay. Now, here is our function reverse string. So there are a couple different aspects to this, and the first one is really a very important one, which is from the beginning, I need to specify what happens when the word is either no characters or has 1 character. If it has 1 character or no characters, what do I do to reverse? Nothing. I just return the word itself. Okay? Now I'm returning by value, so I am making a new copy of the word. Okay? I'm passing in a word by const reference, but I'm returning a new word. Okay? Now, if the word, now I should change length to size. I don't like length very much. I'm going to change it to size. I like size better because both vector and strings have a size function, but only string has a length function. So sometimes students will write length for a vector, and my feeling is I should probably just, I prefer to just write size everywhere because that's what I mean. I mean, what is the size of the string or the number of characters? What is the size of the vector? If you go back and forth with length, you might at some point try to call length on a vector, which won't work. But size will work for both of them. Okay, so if the number of characters is strictly larger than 1, or in other words is 2 or more, then what do we want to do? We want to, here's a plus, we want to take out the first character, right? As a string, but certainly take out the first character and store that as a string variable. So index 0 with exactly 1 character, so the first letter. Then we want to write add that to reverse string with word.substr of index starting at 1, or in other words, starting at the E, and consisting of, oh, I guess I left out the N. Okay, looks like I should have like so. Okay. There we go. Well, and I should make this blue so that, okay, there we go. And that is how the magic happens. Okay, there we go. Okay. Okay, so I call reverse string on a strictly smaller word. So eventually I'm going to get down to the base case where it just returns the word itself, and then the chain reaction goes up. So it's calling a function. And when it finally exits out, it gets out of the function, out of the function, out of the function, and it unwinds. Okay? So you think of this as winding up as it's going down the recursion, as it gets more and more characters, extracting them. And then when it finally gets to one character, it then ends its function, ends, and it winds back down. Okay? Now, the reason why I left out the variable n is because the simpler, better way to do this, well, maybe not better. I wouldn't vouch for better. But here's a simpler way to write it. There's another way to overload substr where, let's see, if you just use a single input value, it starts your substring at that index and goes until the end of the string. Okay, so it's a little bit easier to read. What you're saying is, another thing that you can do too is you can take word of 0 as a character, and you can add it to a string, and that will create a new string object. So it just depends on, stylistically, this seems a little bit more readable. Okay, word of 0 means the first letter. That should be very apparent, or, that we're kind of used to that idea. And then substring starting at index 1, and that's what we're assuming reverse string returns that smaller string in reverse order. Okay. Let's see. Just to kind of bring it back again, you need this base case, this return word. If you don't have a base case, the function will just keep calling itself, and then it never ends. Okay, so that's what's called infinite recursion. Okay, infinite recursion is when a function keeps calling itself indefinitely. Excuse me. I think I did an example with this with point2d and the print function and color point2d, and if you didn't call point2d : print, it would keep calling the color point2d print function and indefinitely. And then it runs until what's called stack overflow, which is where the website kind of gets its name, which is there's only so many functions you can queue up to be called, and then at some point your stack memory runs out, and that's what's called stack overflow, and you get some kind of undefined behavior. Typically a crash. Okay, so let's see how we're doing. So what I usually do at this point is at some point I'm going to transition to the Blackboard for either the Blackboard or if I modify the slides, we'll see. The overarching idea here is the following. You want to solve a problem on n things, call it f of n. So for example, a string with n letters. You're going to decompose this abstractly, not literally like plus or times or whatever, just abstractly as you take away some stuff from the total large string, like the first character. Then you solve the smaller problem with n-1 things, and then you piece back together the smaller solution with the stuff that you took out initially. Okay? And then the base case is sort of like having an f of 0 equaling some fixed value, and that allows you to break the chain reaction. Okay? So this picture is just showing how f of n-1 is going to call f of n-2 with some other stuff. And again, the key is to just know how to recombine everything together. Here's an example with permutations, and if you tried to write this code without recursion, you can do it, but it's just a logistical nightmare. Okay? The code with recursion is so much more elegant and easy to follow. So what is a permutation? A permutation is literally just a rearrangement of elements. Okay? Think of the number, the word YES. Just think of each character as distinct. Don't try and do a word with repeated letters. Just every letter is distinct, let's say. Okay? And we want to look at all possible rearrangements of the letters. Okay? Now, there's, for example, how many different rearrangements begin with Y? Okay? 2 of them. You pull out the Y, you leave that in front, and then you end up with ES and SE. Okay? Or you make the E the first letter. And then what are you left with? You're left with YS and SY. You pull out the S, and what are you left with? YE, EY. Do you see the pattern? Okay? The pattern is pick one letter to be the first letter, and then append to it all what? All rearrangements of letters without that letter. Okay? So in other words, if you want to rearrange all the letters in A, B, C, D, you take out A, and then you find all rearrangements of B, C, D, and you left append A to each one of them. Then you take out the B, and then you rearrange A, C, D. There, 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 there. Then you take out the C, etc., etc. Okay? So therein lies the self-similar structure, which is take out a letter, and then find all permutations or all rearrangements of those remaining letters, and then append in front of each one of those the letter you took out. Okay? That's okay. That's what I just said in words. Okay, here is sort of the code. There's a lot more comments here than I need, and I didn't actually write the lines of code right here, but let's just take a look at this. Okay, so permutations on a word. So just assume the word has distinct characters for now. Okay. So we need, first of all, we need to check for words with a single letter or an empty word. So for example, if the string you put in was the empty string, well, wait, hang on. Before we do that, what is the return type of this function? A vector of strings. Okay, so we're going to input a string, and as our output, we're going to get a vector of strings. Makes sense, right? YES, we need the vector consisting of all 6 possible rearrangements of the letters. Okay? So let's think about this. When we have a word, let's say it's the letter A that gets input. We don't just want to return a string data type with the letter A. We want to return a vector with one element, right? And that is the string itself. That's the code up there. Okay? Similarly, if the word is the empty string, well, that is still a string object. We want to return that, but inside of a vector. Okay? So we're going to return a vector consisting of that word. And that's it. If the word has one character or no characters, you just return a vector of that word itself. Okay? Now, if you have 2 letters, for example, or more letters, then what do? Well, you then loop through all letters, omitting one each time and permuting the rest. So you take out the ith letter, as we showed in our YES example. So take out the ith letter, call the permutations function on the remaining word. Okay, so return a vector of strings consisting of all possible strings, which are rearrangements of the remaining letters. Okay. And then recombine the ith letter with all of those permutations. Okay? So again, what is the recursive procedure? I want to find all rearrangements of this set of characters. For each character, I take it out, I rearrange the remaining letters, and I get a list of those, and I just left append this letter I took out to each one. And I do this for each letter, and then I recombine everything at the end. Okay? It's a very elegant idea, and we can write code recursively that almost mimics that the three-step procedure. Okay? Oh, it looks like I took it out. Okay. So here's the idea is if we go to pick 10b, and this is lecture, I think this is lecture 9. There's my permutations function. There's a reverse string, and there's a Fibonacci. So let's take this code, and let's just put it in place. Again, I'm going to post this code online that's in here. So let's just get rid of let's get rid of everything up until, there we go, there. Copy and paste that in. Does it compile? Okay, so you have access to this code on CCLE, I think week 1. Okay, so this is to encourage you to just go to the code and play around with it. So for example, here's my permutations function. So I input a string called word, and I'm going to make this a const string reference. And if I do that down there, I have to do it up here. Okay. Now, let's see, permutations of A, B, C, D. So let's create a vector of strings called perms. And we're going to do perms equals permutations. And then we're going to do a for loop, auto reference x in perms, cout x. Whoa. Oops. Get rid of that. Succeeded. And there's all of my permutations. Let's do a larger one. EFG. Okay, and there it prints out all those permutations. Okay. So what is it doing? Let's take a look at the code itself. Here's our permutations code. So here's our base case, right? All permutations on a single letter or empty. Okay, just returns a vector of strings with the word pushed back. Okay. Otherwise, and then it returns, and it doesn't execute anything else. Otherwise, all right, everybody out.